Hi everyone. In today's video's lecture, we are going to discuss on analog to digital converters, commonly called ADCs, with special focus on one very important and very fast ADC known as flash type ADC. ADCs plays a crucial role in modern electronic systems because the most real world signals are analog in nature, but all the processors and the digital systems understand only digital data. So the analog to digital converters act as a bridge between the analog world and the digital world. In the next slide, we are going to start with the introduction about the analog to digital converters. Let us first understand what analog to digital conversion actually means. An analog signal is a signal that can take any value within a range like temperature, sound or voltage from a sensor. A digital signal on the other hand can take only discrete values, usually represented in binary form as zeros and ones. So analog to digital conversion is the process of converting a continuous analog signal into a discrete digital representation. During this conversion process, the input voltage is sampled, the voltage level is quantized, and finally it encoded into a binary form. One important point to remember is that the conversion time depends on the clock frequency used in analog to digital converters. Higher clock frequency generally means faster conversion. Next, the key characteristics of an analog to digital converter. Now let us look at the important characteristics that defines the performance of an analog to digital converter. The first is resolution. Resolution tells us how many discrete levels the ADC can divide the input voltage into. For example, an 8-bit ADC can represent 256 different levels. Next is conversion time. This is the time taken by the ADC to convert one analog sample into a digital output. This parameter is very important in high speed applications. Then we have a quantization error. Generally, the quantization errors are analog signals are continuous and digital signals are discrete. Some amount of error is unavoidable. This difference between the actual analog value and the digital output is called quantization errors. Finally, we consider the input and output specification such as the input voltage range, reference voltage and logic compatibility. These are the characteristics which defines the performance of an ADC. That analog to digital conversion techniques. We have different types of available to perform analog to digital conversion and each has its own characteristics like advantages as well as disadvantages. The first one is counter or tracking ADC, successive approximation ADC, which is the most commonly used ADC. The next one is dual slope integrating ADC. The next one, voltage to frequency ADC, parallel or flash ADC, which is a very fast one that we are going to discuss in the future slides. Then software based ADCs, shaft encoder ADCs. Among all this, flash ADC stands out because it is extremely high speed, and that's why we are focusing on the flash type ADC today. Next, the general diagram of the flash type ADC. Now let us understand what is a flash ADC. A flash ADC is also known as parallel ADC and is the fastest type of analog to digital conversion that is available. Unlike other ADCs which convert the signal step by step, a flash ADC converts the input in a single step. This is possible because it uses multiple comparators working in parallel instead of working repeatedly. As a result, the conversion is almost instantaneous, usually within nanoseconds. Here we have main components of a flash type ADC like resistance ladder, comparators, then binary encoders as well as the digital output. In the upcoming slide, we'll discuss one by the key components of an flash type ADC. The flash type ADC mainly contains three major blocks. The first one is comparator array, the next one is resistor ladder network, and the last one is priority encoder. The comparator array. The heart of the flash ADC is an comparator array. Each comparator compares the input analog voltage with a fixed reference voltage. For an n-bit ADC, we require 2 power n minus 1 comparators. For example, a 3-bit ADC requires 7 comparators. For an 8-bit ADC, it requires 255 comparators. Each comparator gives logical 1 output if the input voltage is higher than the reference voltage, and logical 0 if the input voltage is lower. Similarly, the next one is resistive ladder network. The resistive ladder is used to generate evenly spaced reference voltages. These voltages divide the entire input range into equal steps. All the reference voltages are derived from a stable reference source, usually connected to the supply voltage. The priority encoder. The outputs of all the comparators are not in binary form, so a priority encoder is used. The priority encoder converts the thermometer or analog coded output of comparators into a binary digital output. Working principle of a flash type ADC. Let us understand the working principle step by step. When an analog input voltage is applied, each comparator checks whether the input is greater than its reference voltage. All comparators with reference voltage lower than input will produce logic 1, others will produce logical 0. This creates a pattern where the outputs goes high sequentially up to a certain level. The priority encoder then detects the highest active comparator, converts that position into an equivalent binary number. Since all the comparisons happen simultaneously, the conversion is completed in a single clock cycle. The next, advantages and disadvantages of flash type ADC. First, if you consider the advantages, the flash type ADC is the fastest ADC among all the analog to digital converters that is available, which is capable of converting in less than 10 nanoseconds due to their parallel operation. Then it has a simplicity. The design is straightforward, makes it easier to implement various applications. Then it is simple conceptual design suitable for real-time and high-frequency signals. If you consider the disadvantages, the main disadvantages is component intensive. The number of comparators required will be exponentially increasing when the number of bits goes on increasing. It is impractical for higher resolution applications. Requires large number of comparators. Hardware complexity increases exponentially with resolution. Higher cost, not suitable for high resolution ADCs. The next one is applications. So the flash type ADC are commonly used in high speed applications, especially in digital oscilloscopes, video and image processing systems, radar and communication systems, high speed data acquisition systems. So the flash type ADCs are crucial in applications requiring fast, efficient analog to digital conversion, leveraging simple and effective architecture to achieve high speed and performance. Next, if you come to the conclusion, to conclude, the flash type ADC is an excellent choice when the speed is the top priority. However, due to hardware complexity and cost, it is only used when ultra fast conversion is required. Thanks for your patience. We will again